Okay, we're good. We can see.
Were you talking to me, Nick?
Yeah, I was just telling you, you're up on the screen. We can see. So,
Woohoo! Oh yeah, I need to make sure I'm on the Wi-Fi. The bandwidth doesn't seem impeded in any sense right now, does it?
you are a little blurry, but we're not getting the like bandwidth issue
Okay.
notification.
I just connected to the Wi-Fi, so hopefully that de-blurs me, de-noises me. All right, so it is 11 o'clock, which means that's when I start class. In case any of you didn't know that. So we're jumping into the next section today. I did upload a lecture on YouTube that is the follow-up to Tuesday's lecture. I understand that I got it up a little late because I'm having some Canvas issues, and that's just when I got it up. So if you haven't watched it, I understand. You may be a wee bit caught off guard or lost at the beginning of this lecture because you haven't watched that lecture. So you definitely want to go circle back and make sure that you watch it and see all the exercises, which I imagine you will because you don't want to get caught off guard on an examination or something like that, right? So anyways, we're jumping into 9.8 today, and this is a really important section in terms of general applicability of all this stuff that we've been learning. So if in the back of your head you've been wondering how is this useful, or what, this all just seems so whatever, just like a game with symbols, I'm sympathetic to that sentiment. But here, today's topic and the next couple of lectures topic is of high utility in applications of mathematics. There we go. That's a better marker. Right. So we're going to talk about special critters today called Taylor and Maclaurin series. Really, there are only Taylor series, and Maclaurin series are just a special case of Taylor series. But they go by different names. I'm not quite sure why. Maybe historically they both discovered the same thing, sort of like Rolle's theorem and the mean value theorem. There's no reason to teach Rolle's theorem because the mean value theorem summarizes all of it, but we still do it for some reason. So same thing's true. We still teach Maclaurin series in addition to Taylor series, even though they're kind of just a special case of a Taylor series. So I remember when I started learning this in Calc 2, I kind of was excited because it just sounds sexy. Taylor series, Maclaurin, there's names, it sounds like some specialized information. And in some sense, it really is pretty sexy. So let's get to it. One of the insights we got from 9.7 was that we can represent a function as a series. And we really didn't put many restrictions on this, hopefully it's continuous, hopefully it's differentiable, all those things, but we didn't really make any strong statements about that. But today we're going to assume that our function is what we call smooth in the parlance of mathematics, which means it just has as many derivatives as you want. You can continue to take derivatives of this sucker with no issues, right? Some functions that is not true, and for some functions that's only true at certain points. So, what is it? Think of the absolute value function. This isn't really important, but just as a small example, we usually trot out the absolute value function as an example of something that is continuous everywhere, but fails to be differentiable at the origin. And so, the absolute value function is smooth for any point outside of the origin, but fails to be even differentiable for fails to even have the first derivative at the origin, right? So there's a sense in which we can say a function is differentiable, infinitely differentiable or smooth everywhere, or at a point. And for the sake of Taylor and Maclaurin series, we're going to assume that our functions at least is smooth. Generally, it's smooth at a given point. Which point in particular? At the center of the series, right? So I'm not going to leave this up here. This is just me talking at you. But let's make sure we got our terminology right. This is a power series centered at A. And we're saying with this expression that this power series converges to this function. So we can represent the function as a series. Now, one of the things that I discussed in the lecture yesterday that you may or may not have watched is that assuming the function is differentiable, then we can compute or represent the derivative of the function in terms of the derivative of the series. So if I want to know who f prime is, I can represent it in terms of the derivative of the series, and the series is just a polynomial, right? But it's not trivial to say that I can take the derivative of this thing because it's an infinitely long polynomial, potentially infinitely long. So it's not trivial, but I won't have to actually motivate the fact that we can do this. Just take it as gospel. You can take the derivative of infinite sums. And how does that derivative work? Just like it would for a regular polynomial, not an infinite polynomial. Like if we just ignore the sum, what are we going to do if we take the derivative of this? We're going to bring down the exponent and then subtract 1 from the exponent. Okay. So, and one thing that can happen is that when we do that derivative, we lose one of the terms in the sum. So if we expand this sum, when we plug in 0, the very first term, a0, will die. Everything will die here because I have a factor of n here. So it starts at 1, and if I expand the sum, I'll get a1 plus 2a2 x minus a to the 1. And then if we look at the next one, it'll be 3a3 x minus a to the 2, etc. So we expand this guy. And I could likewise have done a similar expansion just for the regular function, which I'm going to write up here real quick. So we have it all laid out. So if I expand that function, it would have been a0 plus a1 x minus a plus a2 x minus a squared, so on. Okay. So I can keep playing this game, just taking derivatives and looking at the sums, the expanded sums. So we can take the second derivative. And if we look at it as a series, it'll look like this. We'll take an additional derivative. We'll bring down the n minus 1. There already was an n. And then we'll subtract 1 from the exponent here. And so since this sum has a factor of n and n minus 1, the first non-trivial term doesn't occur until we get to n equals 2. So if I expand this guy, when I plug in n equals 2, I'm going to get 2 times 1 times a2 plus, when I plug in 3, I'll get 3 times 2 times a3 x minus a, and so on. So you can imagine someone, they start tinkering with this idea, like, oh, okay, what happens if I just take as many derivatives as I possibly can? I'm assuming that I have as many derivatives as I want. So what happens when I go all the way out to, say, the nth derivative? And when we're taking the nth derivative, we denote that with an n, and there's parentheses here. So what does the nth derivative look like? Well, we start seeing a trend here where if we look at the first term for each derivative, and the function itself, the first term, which is the only constant term, every other term has a factor of x minus a. If we kept expanding it, and I didn't want to waste a bunch of real estate doing that, we'd see a pattern emerge. And that pattern would be that for the nth derivative, the very first term, which is our constant term for our polynomial, would be n factorial times a to the n. And then we'd have a bunch of other stuff of order, things with factors of x minus a, and so on, in higher orders.
Wait, so why? Is A1 backing out?
Here?
Yeah.
Right. So, I mean, just all you're doing is plugging in. When you plug in 1 into this expression, you'll get a1 times 1 times x minus a to the 1 minus 1. So that's 0, which turns that factor into 1 and leaves you only with a1.
Okay, but then when it's. But a equals 1 just doesn't exist at all
Say that again?
for the second Taylor series.
The second derivative here?
Yeah.
You're saying a1 doesn't exist at
Oh,
all?
wait, never mind. I got it. I'm tracking now.
You're tracking now, right? So every time we take a derivative, because we have these coefficients growing here, they're going to kill a term, right, in the expansion. So yeah, we're losing 1 every time. We start with an a0, then we only have an a1, then we have an a2. And so when we go out to the nth derivative, the first term will be the nth term. All the earlier terms all are killed, because when we plug in n for any lower number, it'll kill the term. So we do this pattern, we see this pattern, and notice that for the nth derivative, we get this one constant term, and then everything else has a factor of x minus a. And this is just sort of a not particularly rigorous way of writing. We've got everything else in the sum, right, which is infinite, but everything else in the sum has some factor of x minus a. It might have an x minus a squared, an x minus a cubed, whatever, but it has some sort of x minus a to it. So once we make that observation about this pattern with the derivatives, then we can say, oh, check it out. If I take my nth derivative of f and I evaluate it at the center, then that's going to kill everything downstream of the constant term, right? Because everything here has some factor of x minus a. So when I plug in a, I'm going to get 0, and everything's going to die downstream. So the only thing that's going to survive is the constant term. Which is pretty nifty, because this gives me a way of expressing analytically what my nth coefficient is. So I can rearrange this formula and say the nth coefficient should be the nth derivative of our function evaluated at the center divided by n factorial. And so now we can, assuming we have these derivatives, right? There's always that assumption implicit in this. We could have some function that at a is not differentiable, and then this whole thing fails, right? But assuming we have these derivatives, then I can write this expression, this equation for the coefficients And so I can write the series now in terms of these derivatives. And so what does this tell me? This tells me that if I want to write the function down, right, which we know if we were to expand it, that'd be a0 plus a1 times x minus a plus a2 times x minus a squared, that I can substitute in for each of these coefficients this expression here, right? So this would be the function evaluated at a divided by 0 factorial, which is just 1. Then the first derivative evaluated at a divided by 1 factorial, which yet again is just 1. And I could go all the way up, say to the nth term, and that's going to be the nth derivative evaluated at a n factorial x minus a to the nth power, and then there'll be more terms downstream of that. So if I put it very succinctly, I say my function, yeah, y'all can see that, is equal to the sum of f, here I'll put a k, the kth derivative of our function evaluated at a over k factorial times x minus a to the k, where k starts at 0 and goes to infinity. So that process we just went through isn't terribly, I don't know, I mean, it's almost something that even at your level, you could have potentially figured out once you started playing around with derivatives and said, hey, look, I can do this, and then I can rewrite this. It's almost obvious once you see it, like, oh yeah, that makes sense. Okay, cool. But then, you know, kind of what's the point? That, I mean, it's interesting, but what's the point? Well, we'll see the point. So first off, what we just derived, that was a derivation, which maybe if you're in a physics class, you're familiar with derivations. They like to derive things at you all the time. We just derived the definition of a Taylor series. So what is the Taylor series? The Taylor series of, or I guess what the terminology is, generated by a function f that is smooth, which just means infinitely differentiable. I can take as many derivatives as I want at x equals a. The Taylor series generated by a function f that is smooth at x equals a is precisely what we just wrote down. F of x is equal to that sum. Okay, so I mean that's all the theory there is to it, and in fact, it's clear enough at your level that you can see the derivation of where this thing comes from. And like I said, there is this other critter that we call a Maclaurin series, and that's just a special case of when the center is 0. So all the same stuff, but at x equals 0, where we're centered at 0. And if I write that down, we don't have to change much. We're just evaluating the derivative at 0. And then here our term is just x to the k, since a is 0. So this really is just a special case of a Taylor series. That being said, because it's, you don't have that x minus a factor, this is just considered a little bit more elegant, and we often reach for Maclaurin series more often than we do Taylor series. And in some sense, we can always take a function and shift it horizontally so that we can center it at 0 and just talk about its Maclaurin series. So, it's, to be rigorous, we have to present everything, for any sort of center, but Maclaurin series are usually sufficient to characterize any function because I can always just translate the function, any function that I'm interested in, and make it center 0. Right. So that's the definitions. I mean, that is like the full extent of what you like, the new information from 9.8. Now we are just going to look at finding these guys, right? So if you're given a function, can you find its Maclaurin series or its Taylor series? Or in some cases, maybe you're given the series, can you find the function, right? So let's look at an example. So these prompts will usually go something like this. Find the Taylor series for f of x equals 1 over x at a equals 2. And then, the follow-up question will be, where does it converge? Right. So you're going to get used to this. You're going to do enough of these that you'll get to be crackerjack Taylor series discoverers. In order to do this, we need to find sufficient derivatives that maybe we can see a pattern in the coefficients. So we're gonna take a number of derivatives. We're gonna plug in the center and see what sort of pattern we get, and maybe we can write that down in a very nice and neat way. Let's give it a go. So first we'll look at the first derivative. First derivative of 1 over x is just negative 1 over x squared. So if I plug in 2 into that, I'll get negative 1 over 4. And sometimes it can be useful just to leave it as 2 squared, just so you can see the pattern. You'll have to play around with it sometimes. So that's f prime evaluated at 2. Take a second derivative and evaluate it at 2. Just being pedantic here. Okay, so we'll take the second derivative, and that one's going to be positive 1 over x cubed. And that should be a 2, right? So we can write it as x to the negative 2, take the derivative, bring down the negative 2, it kills the negative that was already there, becomes positive, and then we subtract 1 from negative 2, gives us negative 3, so this is what we get. Now we're going to evaluate that at 2, and we're going to get 2 over 2 cubed. And maybe like I said, you don't know what will aid you in finding the pattern quite yet, but this obviously simplifies to positive 1 over 4. Maybe that will help us. Take a third derivative and evaluate it at 2. So what do we get? We get 2 times 3, but it's negative now. And what I'm going to do, because I can already see the pattern starting to merge, is I'm going to write 2 as 1 times 2. And then here we'll have negative 1 times 2 times 3 over x to the 4th. Then we're evaluating that at x equals 2. So if I write this, I'll have negative 1 over times 2 times 3 all over 2 to the 4th. All right. So does anyone want to wager a guess what the nth coefficient is going to look like at this point? Can you see the pattern? Can anyone see it or see any part of a pattern? You don't have to spit out the perfect answer. You can also just spitball. We're brainstorming here, right? One thing I want to say about mathematics in general, just before anyone answers, is that like real mathematics doesn't when you're doing research or working out hard problems, it doesn't consist in always making one complete monolithic utterance that captures everything. A lot of it's just a couple steps forward, one step back. Everyone's kind of hacking at it, trying to figure out something. So don't feel like you need to, whatever you say needs to capture everything. You can say, well, I kind of see something like this going on. That's perfectly adequate response at this point, right? So what does anyone see any sort of patterns here?
You just suggested 1/4, is that what you said?
What's that?
Rouge just suggested 1/4.
1/4. So I mean, certainly we see something like that here. Now, if we computed it, what's that?
This is factorial in the numerator.
Aha. Okay, so that's a critical observation. Here I've got a 1. Here I've got a 1 times a 2. Here I've got a 1 times a 2 times a 3. So we might surmise that the nth coefficient will have at least what part? One component, which is what? Go ahead, Jackson.
And exclamation mark.
What's that?
And exclamation mark.
N factorial, right? So we're going to have an n factorial. Does anyone else see any other patterns here?
Power of the numerator is increasing.
The what?
The
The denominator power in
Yeah.
the denominator is increasing. So be more explicit. What else do you see? Not just that the power is increasing, but what is the denominator? The power of what is increasing?
2.
2. So what do you expect the nth one will have? If this is the third one and it has a 2 to the 4th, and this is the second one and it has a 2 to the 3rd, then what do you think the nth one will have?
2 to the n plus 1.
Perfect. 2 to the n plus 1. Any other observations?
You see that the sign changes.
Very good. So what do you call that, Ian? You see the sign changes. What's the appropriate terminology for that sort of behavior? If we have a series whose terms are changing sign, what do we call that?
I mean, you call it alternating.
Alternating. Good.
Yeah.
Yes. So if you said that, I just didn't hear you. So
Oh,
just speak up. So we also have something that's alternating here. Now that means we're going to have a -1 to the power of something. We have to be careful that we write it down right. So when n equals 1, we get a negative. When n equals 2, we get a positive. So that means that when n is odd, we get negative. When n is even, we get positive. So we should be able just to put an n here. And that will capture the alternating nature here. You always got to be careful because you're relating what you see here to what you see here, right? And so when the index is n, our coefficient, the sign of our coefficient should be -1 to the n. So that is the game we're playing, is we're finding that pattern. And sometimes you might have to take out more derivatives to see it. This one I thought kind of fell together pretty quickly. If you don't see it immediately, don't worry, take another derivative, see if you can't find it. Now, one thing that is important is that what really enabled us to find the pattern was not simplifying, is keeping everything sort of in its most expanded form. Because if we had simplified everything, we might started seeing something else that we couldn't quite describe easily, right? So writing out the -1/4 and the 1/4 might lead us to think, oh, it's just an alternating sum of 1/4 or something, you know, but no, it's not that simple. So it's not always helpful. Maybe it could be helpful because it could simplify to the same number every time or something, but I think we would find pretty quickly that that's not the case here. But we've got a pattern for the coefficients. And we are able to write down that pattern in a closed form, so just in terms of n's. So now, if I want to write down the series, the Taylor series for our function, I'm going to use k's now. K is going to start from 0 and go to infinity. And the coefficients are going to be -1 to the k times k factorial all over 2 to the k. And then we're expanding this series around the center 2. So we'll have an x minus 2 to the k. So that is our that is the Taylor series for this function, right? This part for me was a lot of fun when I was first learning it. Figuring out these patterns, I really enjoyed that process. And as I've said it multiple times, when are these things, all this math that we're learning, what are the applications? And one of the key applications that always comes to mind is finding solutions to differential equations. And this is the sort of game that you will end up playing, is you'll try to find a general solution to some complex equation, and you'll get some sort of relationship in the coefficients, and you'll have to find the pattern, and you can write something like this down. Now, once you write something like this down, it may not be obvious that f has a name. It might not be a sine, it might not be a cosine, it might not be a natural log, it might not be any sort of function that you can name directly. But you have an expression for it here. And there's quite a bit of things in mathematics where the best we can do is write down a series representation of a certain value. So, like go look up the gamma function if you're interested. The gamma function is an example of something, I believe, if I'm remembering, where we can only write it down as a series. Bezel functions are another one. There's all types of functions like that. Right, so the second question was, the follow-up was, where does this thing converge? Where does f converge? And that goes back to what we were doing on Tuesday, looking at finding the radius of convergence for the series. Right, so how did we do that? We did a ratio test, right? And that enabled us to see what was going on. So let's look at a ratio test. Limit as k goes to infinity. The alternating component will go away. We don't have to worry about that. So what are we going to have? We're going to have a k plus 1 factorial x minus 2 to the k plus 1 all over 2 to the k plus 1 divided by k factorial x minus 2 to the k over 2 to the k. And then we simplify. The k factorials are going to cancel out all but the k plus 1 term or factor. We're going to end up with 1x minus 2 left over. That will remain an absolute value. And then we'll have just a 2 down in the denominator. All right. So what do we think? What is this going to do as a sequence?
If we put in k equals infinity, it should diverge to infinity. But then
Right.
we have x minus 2 term.
Mm-hmm. So we saw this example before. So if we're thinking about this in terms of what values of x, depending upon what values of x I choose, what will happen with the series? Or I mean, with the sequence here. So in general, for most x values, this thing is divergent, right? So this thing goes to infinity if x is not equal to 2, and goes to 0 if x equals 2. So that means that this series that we've written down is only convergent when x is equal to 2, which means it's not super useful. It's correct. It's not super useful. So f of x, or we can say our series, converges absolutely at x equals 2. And that's it. That's our radius of convergence. And we shouldn't be surprised again, because when we look at this series, we've got a factorial in the numerator and a exponential in the denominator. So there's no way this thing can ever slow down. It's just going to, that factorial is going to outgrow everything. Okay. So that is Taylor series, Maclaurin series. What else can we do with these things? One way that they're absolutely useful is as a tool for approximating functions. So we define something called the Taylor polynomial of order n generated by f as the polynomial p sub n of x. And I guess, this should be centered at x equals a. Then the nth order Taylor polynomial is just the truncated series, where we truncate it for all terms past of n plus 1 or greater. So plus ... So in other words, it's a partial sum. It's a partial sum of the power series, and it approximates the function, just like a partial sum approximates the series. This partial power series sum approximates the function, right? So there are really great reasons why we might want to work with this over this, right? Derivatives of this may be hard to compute. Derivatives of this are relatively easy to compute because it's just a polynomial. You know, derivatives of polynomials don't get much easier than that. This thing will have singularities, meaning there are things where if I plug in 0, it'll blow up, but this is just a polynomial. It doesn't blow up. But there's a caveat here, which is I say this approximates f, but only around the center. So the quality of the approximation is best the closer you get to a. So really, I should say it approximates f around x equals a. So what do I mean by that? I mean, suppose I'm just going to make something up. Suppose my function is x squared. And then I find the first order Taylor series around, or Maclaurin series, let's say centered at 0 for x squared. So what is that going to be? That's going to be x squared evaluated at 0, which is this 0, plus the first derivative of x squared, which is 2x evaluated at 0. Okay, maybe 0 is a bad example. I'll choose some other point. Let's say 1. So let's say centered. So let's look at P. I'm trying to find out where to write this. P1 centered at 1, right? I guess I should say that. It's P1 of x, but centered at 1. So what will that thing look like for this function? We'll plug in 1 into f. That will give us 1. And then we'll take the first derivative, which is 2x, evaluated at 1, which is just 2 times x minus 1, and that's it. So that's the first order Taylor polynomial for f equals x squared centered at 1. So if I look at 1, what is this thing going to look like? I mean, if I graph this thing, just simplify it real quick. This will be a linear function, 2x minus 1. So if I graph it, it's going to look something like this. And it should end up being tangent to the curve. So, and it should intersect right at 1. They should be equivalent. So what do I mean? This approximates it well around A, around the center. If I zoom in on this thing, then I'm going to have the curve of f equals x squared, and then I'm going to have a little bit of a linear function, right, tangent to it, and it touches it right at 1, and then it starts deviating from it above and below 1, right? So there's some error in the approximation, but it looks pretty good. And if I zoomed in even closer, then I would see a flatter piece of the function, and that line would be really close to it. And if I zoom in infinitely close, then they'll be identical. So obviously, this is a bad approximation globally. It doesn't look anything like the function, but locally, right around the center, it's a pretty good approximation, right? Now, if I keep on adding more terms to this, it's going to get more curvature, and it's going to start approximating that function better and better and better. And it's the magic of a Maclaurin or a Taylor series is that if I look at all of those functions, I start off with a linear, then I'll get, in this case, I'll converge and I'll converge as soon as I go out to the second order. But if I look at all of those functions, I'm adding up a bunch of different polynomials. And if I do that out to infinity, there's magic thing happens where it turns into the function. I mean, it's just absolute magic. And this is the basis of a really, really super useful topic called Fourier series or Fourier analysis. And when in Fourier series or Fourier analysis, we're not doing this with polynomials, right? We're not approximating a function with polynomials. We're approximating a function with sines and cosines, with trig functions. So we can do this with any kind of function, and Fourier series is all about that. And if you're into engineering, if you wanted to go into electrical engineering, you're going to do a lot of Fourier analysis because it's really good for signal processing and signal analysis. Okay, so one special note, make sure I was looking at the time, we're getting close. One special note here is that we say Pn of x is of order n because we don't know what the value of the derivative will be out to n. So it is totally possible that the nth derivative of the function that we're approximating evaluated at the center will be 0. Which means, so this could happen, but that would imply that the resulting polynomial would be of a degree, the degree of the polynomial would be strictly less than n. So we say order because it could be up to the degree n, but it may not be exactly of degree n. So it's a slight subtlety, but something worth bearing in mind. And in fact, the little example I was just doing is a great example. If we look at let's just say, what is P3 of x here, and we'll say centered at 1. What does it look like? Well, we already know the first two terms. And then we add, so that's P1. What will be P2 have? It'll have those plus another derivative here evaluated at 1. Well, the second derivative of this is just 2. Great. And then we'll have a x minus 1 squared. And then I'll take the third derivative. Well, that's just 0. And that's x minus 2 cubed. So this simplifies to 1 times 2 times x minus 1 plus 2 times x minus 1 squared. So obviously this polynomial is of degree 2. It's not of degree 3. So the third order Taylor polynomial is only of degree 2 for this particular function. And might be interested to see what happens if I expand this out. And combine like terms. 1 minus 2x plus 2 plus 2x squared minus 2x plus 1. So what happens? I've got a, oops, did some bad math. That's 4x That's 2. So what's going to happen? We're going to have a 2x squared minus 2x minus 4x. That's minus 6x. And then we have 1 plus 2, which is 3, plus 2 is 5. So we end up with a quadratic function that is not f of x squared, right? So this is still an approximation to the function. I forgot there should have been a 1 there. But it is of the same degree of f of x squared. Now, if we had done this at 0, if we had expanded it around 0, we should have ended up back with the original function. But I guess that's it. Yeah. So we'll do more Taylor series, more Maclaurin series tomorrow in class. We'll find these things for all types of different functions. It'll be fun. We'll be hunting for patterns. So hope you guys have a nice day.